Good afternoon. Happy to be here. Yeah, so I'm from NTU in Singapore. So you know, this is one of the very recent building that we have in the campus. It's called a hive, like the beehive hive. Okay, this is basically a learning hub. A student can go there and attend their tutorial, their recitation, and they can even do their homework here. All right. So if I'm in Singapore NTU, make sure you go and visit and take a picture of that. So what I'm going to be describing for the next 20 minutes or so is about a technology platform that I believe if we are successful, then we are going to have molecular sensing at low cost and also in a very compact form factor. Okay, so hopefully I can convince you at the end of the day that germanium is going to be the new silicon. Okay, they're all group 4, right? But let me start with some grand challenges that we are facing today. Some of them actually make our life a little bit less convenient. Some are actually life-threatening, right? And I think about it, right? What can we do about the detection and sensing of this pollution or also contamination? Most of the time it's done by the expert with bulky devices by the authority, right? So the question that I have here is that if I have a technology that I'm able to give it to you and me as a consumer, as an end user, to empower you to do detection and sensing at your end, then I think the story can be quite different. And this is the technology that I'm going to be talking about this afternoon. So I think like most of you had talked about this this whole day, right? As soon as I can do miniaturization with an integrated approach, then essentially I gain two very important things in my approach. Imagine that I can miniaturize this. This is a spectrometer. It comes with a lot of optical components. Imagine I could do that on a silicon using germanium, right, as an active layer. Then by certain monolithic integration approach, then what do I gain? I gain essentially a significant reduction in the form factor, and that is important. Okay? But what is also more important is that I also enjoy a significant reduction in my cost of ownership. And that's exactly that we are trying to pitch to you about integrated photonics for molecular sensing. So maybe I'll just describe to you how a simple construct of a molecular sensor can look like using photonics approach. This is a very simple view of a sensors technology. Essentially, it comes with all the electronics component that you need to have in order to drive the signal, in order to do the signal processing or so. But if you look carefully, there are a few very major components that are involved. First of all, you are going to need the light source, call it a laser if you want. It could also be an LED if you are not willing to use laser. And then there's a detection photo detector at the end. And what you have here essentially is a series of what we call passive devices. These essentially are just waveguide. Okay? Think of it as fiber optics but integrated on silicon using a silicon or germanium that I will talk about, right? And as the light is traveling through this waveguide, what happens is that you start to generate what we call the evanescent field. These are the leakage light from the waveguide. And if this evanescent field is interacting with the molecule, and if that happens at the right wavelength, then strong absorption will happen depending on what type of molecule you are talking about. Okay? So depending on what type of molecule you are talking about, different molecule will have different what we call a fingerprint absorption in as far as light absorption is concerned. So if you are hitting the right wavelength and the right molecule, then you are going to see a drop in your signal strength at the detection end. So this is a basic idea of a silicon photonics sensors chip, and this is the technology that I'll describe to you. So I'm interested to basically sense the whole bunch of molecule here because it matters to me. What can I do with that? All right? So if I look at this, what we call the transparency windows. Now, the most mature technology that we have today is that of silicon on insulator technology, the SOI technology. It's a wonderful technology. It works very well for the 1.55 telecom transceiver applications. And people are thinking about using that technology actually for molecular sensing as well. And let me tell you what are the issues here. If you look at the silicon on insulator technology, this insulator often or not is actually silicon dioxide SiO2. And silicon dioxide, as you can see here, has very strong absorption starting from about 3.5 micron or so. So the oxide is going to start to absorb the light at about 3.5 micron and above. And what does that mean is that you are going to be very limited in terms of the windows of detection that you can have. So that is not a good technology to use for molecular sensing. So people are moving to what we call germanium on silicon. So as soon as you do that, then you are limited by what silicon can do, which is about 8.5 or so. So that's wonderful. You open up the windows already, you can detect more, so that's good. Okay? But the issue here is that if you look carefully, germanium and silicon has very similar reflective index. So when the delta N is not huge enough, what it means is that you're not able to confine light very efficiently in your germanium waveguide that you see here, right? You are going to bound to a lot of light leakages, and that is not good because that is going to interfere with your signal and power transmission. So anyway, the proposal that we have here is that instead of doing a germanium on silicon technology, can I do a germanium on nitride technology? And that comes with two advantages. The first advantage is that now I'm limited by the transparency windows of nitride, which is about 7 or 8 micron around here. And also, there's a huge difference in terms of reflective index between germanium and nitride. So now I'm talking about a comparable delta N with that of SOI. And now what it means is that I'm able to confine light very efficiently in my germanium waveguide. And when that happens, I can basically bend my germanium waveguide very, very tightly without suffering too much light leakage. That's what we are trying to tell you. And that can be a lot of advantages. What it means is that I can make my waveguide, my sensor structure to be more compact, right? So just for those of you who are working at wafer fab, I just want to assure you that this process is completely silicon compatible, it's totally scalable and manufacturable, and let me show you why this is so. So the way we achieve this germanium on nitride structure is by this process. Basically it's a transfer process. We start with two wafers. This is called a donor wafer, this is called a recipient wafer. If you want, you can call it a substrate wafer, you can call it a handle wafer, anything you like, right? So the next thing that we did is that we actually grow germanium on silicon. This is a direct growth without any buffer layer. So very naturally, you are going to have a lot of crystal defects at the interface. Okay? So bear with me for now because I'll go back to that and tell you how can I now get rid of those defects. Next thing that we did was that we deposit silicon nitride because I need to use silicon nitride as a cladding layer. And I end it with what we call a bonding layer. This is typically just SiO2 material. And then the next thing that I did was basically I put the two wafers together face to face and then I bond them together in a stack. The next thing that I need to do is basically to get rid of this silicon donor wafer, and that can be easily done today in any fab environment. So go ahead and do it, and now you expose the germanium. Now remember I told you earlier that there's a lot of defects on the germanium interface between germanium and silicon. So now that I'm exposing the defective layer, I have the opportunity to basically either improve on the defect density or get rid of it completely altogether. Okay, I can do that. Okay, so the details, if you're interested, you can talk to me. But now that the surface is exposed, you had the opportunity to do those things. So with that, just want to convince you that it's totally manufacturable, it can be done. This is a wafer that we're talking about. This is a germanium on nitride layer that I was talking about. And this is just to at least convince you that the crystal quality is not any different from that of bulk germanium that you can get from any supplier. So with that germanium on insulator substrate that we have already fabricated, the next thing was to basically go ahead and design the waveguide and the bend waveguide in order to study the transmission loss and also the bending loss of the waveguide. So this is one cross-sectional view just to show you that this is the germanium that I was talking about. It's 1 and 2 micron in the sizes. Why was it 2 micron by 1 micron? Because we want to confine what we call the first mode of light, okay? The first mode, single mode. This is a nitride that I was talking about, and this is where the bonding was taking place. This is basically the band waveguide that I was talking about. So we're interested in two numbers. The first number is that what is your transmission loss, okay, or your propagation loss. The second number is, as this waveguide is bending, how much loss do I suffer, right? So I want to go ahead and do a comparison between the nitride platform and the silicon platform. Now look at the number, it's about 3.4 dB or so compared to about 8.18 for GOS. Okay. So this is a significant improvement in terms of the propagation loss, and bear in mind that this is in dB. Okay, this is actually in dB. Am I happy with 3.35? I'm not exactly too happy about it, but I think there's a lot of things that you can do in order to improve the number. Secondly, looking at the band, for every band that I have, and assuming that this is a 5 micron radius band, you're talking about a 0.14 dB loss for nitride platform compared to about 2.54 for GOS. So I think the numbers speak for themselves, and I think the technology is actually working. The next thing that we did is actually we went ahead and designed this spiral waveguide, in case you don't see it. It's 155 micron by 155 micron. The total length that we have here is something like a 4.2 mm or so in total. Now remember, because of the better light confinement, I'm able to do bending more abruptly compared to the GOS platform. So what it means is that as I'm doing this 90-degree bending, the loss that I'm going to suffer will be much less on the nitride platform compared to that of the silicon platform. So what we did is that we designed this platform, we fabricated the platform, we 3D print a chamber, and we mount it on these sensors so that we can contain the liquid that we are going to test, right? And so this is the numbers, right? Comparing the nitride platform to the silicon platform, we are talking about a lowest detection limit of about 5% in the case of nitride platform compared to 16% of silicon platform. Now, while the analyte that we use in this particular case is actually IPA, it's an isopropyl alcohol. For those of you who are working in the fab or clean room, this should be something that's very familiar to you. You use it all the time to clean your apparatus all the time. And the reason why we are using this IPA and not anything else was because it's not toxic. I had to take care of my PhD student, so that's the first reason. The second reason is because the light source that we have happened to be about 3.8 micron or so, and IPA happened to have a absorption peak in this particular range. But just to convince you that we can do, with a nitride platform, we can outperform that of silicon platform. Am I happy with 5%? No, I'm not. I think we certainly need much better number than that. Can we make the number better? Yes, the answer is yes. So as I'm speaking to you, the student is actually working hard, try to improve the design, look at the process, how can we improve this number a little bit further. Now, assuming that this is all working fine and well, what can I use it for? I can think of several use cases, but I think you can tell me more. One of them basically is, can you test the freshness of your food? Because as the food is turning bad, most of the time it will emit gases that you can basically detect. And remember, I want to give the power, I want to empower you and me, the end user, to be able to do the detection at your end. Electronic nose possibly, water safety, clean water, gas sensing, and I think the list should actually go on. So with that, I would like to acknowledge the funding support from a very important agency in Singapore, the National Research Foundation of Singapore. I'll be happy to take any question if you have. Thank you.